Hello everyone, nice to meet you. My name is Tsunalogue from BRGM. I'm here today with my colleague from BRGM, which is a French geological survey, and we are happy to welcome you for this webinar from the GOBEYOND project. And it's a webinar dedicated to decision support systems for different kinds of geo-hazards. We have 1 hour together. We will have different presentation, and at the end we will take time for the question and answers. Just a warning, just to say you that this session is being recorded. So if you prefer not to be captured in the recording, please keep your camera and microphone off. Very quick words about GOBEYOND European project, Horizon Europe project, about multi-risk impact-based early warning. It started in October 2023 for a duration of 4 years, so we are more or less at the middle of the project. We have 27 partners. 18 full partners and 10 associated partners, mainly practitioners, a budget of around 5.5 million euros, and we have pilot sites and all around Europe and its neighborhoods. The idea behind the GOBEYOND project is that we observe that after different natural disasters, we either there was no early warning at all, or not multi-risk early warning, or early warning not fully adapted to the needs from the practitioners, or not fully integrated into the official protocols. So the idea of the GOBEYOND project is to improve the situation, developing innovative multi-risk early warning systems oriented to actions and to practitioners. So today the objective of the webinar is to give you an overview of some existing solutions and systems we developed in France. At BRGM, so the French Geological Survey, for three kinds of events, of phenomena. First, we will deal with the earthquakes, after that with tsunamis, and at the end, landslide induced by rainfall. So we will focus in France. With most of the solution we will discuss about will be focused on the territory of Alpes-Maritimes in the southeast of France. And at the end, the goal is to give you some insight about the principles, the limitation of our systems, and some insight also about the transferability to other areas. At different scales. Maybe just in this slide a few elements about the wording, because we will deal with different kind of events with different kinetic, so different wording. We will deal mainly with the rapid with the impact based warning during the pre-event time and event time. So in assessing the possible impact of incoming events, we are using words such as early warning, forecasting, or giving estimation of ongoing events or events that just occur. And in that case, we use the words such as nowcasting, rapid response, for example. So We will start with the presentation about earthquake rapid response, and I give the floor to my colleague Pierre Gell.
Thank you, Samuel. So hello, everyone. I'm Pierre from BRGM as well. And I will discuss earthquake rapid response solutions that are being developed at BRGM in the scope of the GOBEYOND project and also in previous development of projects, and also dealing with the issue of local solutions versus, let's say, wider scale solutions like systems that could be developed at the scale of the European continent. So this work also has been prepared by some of our BRGM colleagues and also other partners from GOBEYOND like ECM WF and HEEDS and a Predict service as well. So I'll just, let's say, discuss a bit about, let's say, what motivates the development of such tools. Then a specific tool, SEISAID, that was developed at BRGM. How, let's say, we can integrate it to the GOBEYOND system and platforms. And finally, let's say, how to expand this, let's say, rapid response solutions to European level. Let's say it starts from the, let's say, from the observations that although that earthquake early warning is very promising in the sense that it gives some, let's say, some time to prepare and to, let's say, to act very few time. It's also maybe not feasible in each, let's say, geographic context, and also maybe, let's say, sometimes the lead times are not enough to do any, let's say, useful or impactful actions. And also, as then alternatively, earthquake rapid response is maybe, let's say, more straightforward to implement everywhere. And still it, let's say, it gives, let's say, useful, let's say, actions and, let's say, outputs that can help us to, let's say, limit the impact of the event and to improve our recovery. Especially, so such tools are useful to, let's say, size up the global impact of the event. So we need to have an idea at first of the global scale of the event, and so that you can scale the various levels of emergency response. And also, secondly, on a more refined scale, to have maybe maps of quantitative spatial indicators in various areas so that, let's say, first responders can hierarchize or, let's say, prioritize, let's say, dedication of teams and resources in, let's say, specific areas. Yeah, so here on the right is just an example of the, let's say, the various, let's say, possible time scales on, let's say, on the cyclic, yes, on the cycle of, let's say, seismic activity. So you have the event here, and rapid response is really right after the earthquake has hit. So from a few minutes, hours to a few days. And the main principles of this approach is that first we have to detect the seismic event. Then, depending on the coverage of a seismic network, we can collect ground motion parameters and also macro seismic testimonies. And from this, we can generate an intensity map that is calibrated on this observation. So this is called a shake map. And then on top of this, we can, let's say, perform a damage assessment of built areas thanks to exposure and vulnerability models. And finally, generate spatially distributed damage and loss indicators. And so this is precisely the, let's say, the principles that are behind the seismic tool that is being developed at BRGM, the SEISAID tool, sorry. So the objective is to estimate rapidly, let's say within maybe a 30-minute time frame, reliable trends of the earthquake's consequences. So several versions have been developed. So some research demonstrators in mainland France, in the Pyrenees mountain area, and also Southeast France, and also fully operational systems in overseas territories. So one in the French West Indies and one in the island of Mayotte in the Indian Ocean. And so precisely for the pilot site of the Alpes Maritime in the GOBEYOND, we will rely on the, let's say, this pre-existing version of SEISAID for the Southeast France. So this tool was also developed in a collaboration with the research lab geo-hazard. So here is the chain of events that, let's say, are sequenced after the occurrence of an earthquake. And the geo-hazard is taking care of the whole part about generating the shake map from the gathering of recordings from the seismic network, the event detection and characterization, then a generation of the shake map. And then BRGM takes this product and performs the loss estimations, generates an event report that can be sent to institutional partners. How it works is that, let's say, we need, let's say, maybe two main types of input data. So like I said, we need a shake map. So in this case, for the maritime area, we use a shake map in macroseismic intensity. So that has been, let's say, that is created by geo-hazard. And it has the benefit of having, let's say, thanks to their specific seismic network, they can have a general accurate earthquake characterization. Also, they have a high resolution map of site effects. And also everything is calibrated in terms of ground motion models and so on, so that this product is quite reliable and accurate. And in parallel, we also use an exposure model of built areas. So for residential buildings, this is a building inventory at INSEE Iris zones. So this is a French, let's say, district, statistical district that is a bit like an infra-municipal level. And it's based on a risk UE taxonomy of buildings. And yeah, it is only limited to residential buildings. And from these building types, then we can assign vulnerability indices. And we apply then a macroseismic semi-empirical vulnerability model from the risk UE approach. And then based on the, let's say, the macroseismic intensity level, using this vulnerability model, we generate damage distribution in EMS 98 damage grades. And also another product is that thanks to a damage to casualty model, we can also propose estimate of distribution of injuries and casualties. And then this SEISAID tool was at first designed to, let's say, disseminate very specific impact indicators that answer operational needs. So number of collapsed buildings, we need to evaluate needs in terms of search and rescue teams, and also the number of injuries to evaluate needs in terms of emergency healthcare. And then outputs are delivered at municipal level, so that also this usually these administrative levels fit the existing governance levels and the crisis management procedure. So here on the right is let's say a dummy example of the test example of this type of bulletin that is sent to officials and to civil protection authorities. So how we integrated this product in SEISAID is that we are now in the process of completing a web service API between BRGM and Predict services. And then the output variables are various layers of GIS data. So number of buildings in EMS 98 damage grades in each area, and also number of people with injuries, casualties, with also different categories. And here the spatial resolution, we can be a bit more precise and so delivering outputs at the level of IRIS zones, so infra-municipal level. And also there is the possibility of a scenario mode also. So not only, let's say, near real time, but also on demand, you can generate a test if you want to perform exercises. And so this is just an example scenario with distribution of buildings in the maritime areas. Also just a zoom here on the Cannes municipality, so the city of Cannes. Also so that you have an idea of the level of detail of the IRIS zones, you know, let's say how many IRIS zones there are in a big municipality like Cannes. And now the question was, once we had this, let's say, this local product, the idea also in GOBEYOND was to see what we could do at European level, because we had to propose a solution for pilot size that are not covered by any rapid response tools. And also maybe ideally having a harmonized baseline tool for whole Europe. Also that takes advantage of, let's say, existing state-of-the-art models. And also, yeah, of course, when you have, let's say, cross-border events and so on, to have also this whole cross-border process. So the idea then was to, let's say, to take benefit of two existing, let's say, models and tools or services. So first one was regarding shape maps, is the shape map EU service. That is, let's say, also, let's say now operational, and that you can access the shape maps that are generated for Europe. And also the exposure model that was used for the European seismic risk model, ESRM 20 in the EFR risk project. Also that they have data, the exposure at a European level. And then we can use these two outputs in our, let's say, SEISAID architecture, if you want. So first, shake map in microseismic intensity that are directly taken from shape map EU. So what is nice, so like I said, they have European coverage. In some countries, they can use very, let's say, state-of-the-art models in areas like in Switzerland or Italy, where a lot of developments have been made. And then also in areas, in countries that maybe they are less advanced in this shape map system, they are relying on by default assumptions, but at least there is a harmonization between countries. And also for exposure models, so we took the exposure catalog from ESRM 20, and we had to do some, let's say, post-treatment conversion of the catalog to also have inventory at cells of 30 arc seconds. Also, we simplified the building typologies, having only 44 macro taxonomy groups. And also, for now, we're currently only taking residential buildings. Why we did this is because, as you can see on the damage and loss assessment process, it's exactly the same as the one that is used for SEISAID. So the inputs are completely, let's say, calibrated and formatted to be used by the same, let's say, a computing engine, if you want. So this is a nice feature also. So we can use either local or European inputs on the same algorithm. And this has been also, let's say, added in the GOBEYOND system. So in the setup in the cloud processing core from ECM WF, where let's say we send queries to the shake map EU service, we gather shake maps when they are available, and then everything is computed. Let's say the computing algorithm for damage assessment is being run on the processing core from ECM WF. And we output several, let's say, layers of data at cell level or at municipality level. And then they can be visualized in the GOBEYOND platforms from the partners, HEEDS, Predicts, and Draxis. And here, just a detail also about the, let's say, common outputs. So also here we have a various, let's say, possibility to let's say, if you want to display damage data, moderate damage, depending, let's say, on the strength of the earthquake, or really heavy damage, and also the, let's say, the level of, let's say, the proportion of people with injuries, the proportion of casualties, and also the proportion of people needing shelter. So this is also an indicator that is useful for civil protections to know exactly, let's say, how many emergency shelters will be needed and so on. And outputs are generated at, I say here, municipal level, but actually we took the map of local administrative units at Europe for Europe. So this is the resolution level that we use for outputs. So here's an example of a recent earthquake in Greece, and also the more damaging earthquake from Petrinia in Croatia in December 2020. So this is the proportion of buildings with at least moderate damage, and this is a proportion of buildings with at least very heavy damage, so damage state D4 or D5. And here we did also some, let's say, some comparison study with observed the damage data and simulated damage data and checking assumptions also with what we output in terms of the damage grade distribution and how they can fit, let's say, more, let's say, generic indicators from we had catalogs from of a damaging earthquake. And only variables they were discussing were damaged buildings or destroyed. And also, it's an issue to let's say to know exactly what it means. You know, is it only D5 or D4 plus D5 and so on? So we are still, let's say, trying to understand this and testing the outputs. And the same also for the casualties. So here again, comparison with observed data and estimated data. So I just finished. So I've shown you, let's say, some solutions for earthquake rapid response at both local and European levels. Here with a strict focus on the building damage and impact on population, because we are aiming here at the prioritization of operational actions. And let's say also maybe one takeaway point is that the outputs are, let's say, computed at municipal or infra-municipal level. Still, there are, let's say, issues to take care of, like integration of uncertainty treatment. The whole chain is, let's say, is full of uncertainties and assumptions. So also on how, if we do this, how can we communicate on these uncertainties? And like I said, we are still testing and trying to validate outputs. And then a further step would be about, let's say, maybe also doing a damage and loss assessment on overexposed system, for instance, critical infrastructure. And also now that we have this database of exposure, can we also apply similar databases to other hazard types and so on to expand also the damage assessment to other hazard types in GOBEYOND? So I'm finished for regarding the earthquake part. So now please, Samuel.
Thank you, Pierre. So we were dealing with the question of unpredictable events such as earthquakes. So with the system for rapid response, a few minutes, let's say within the hour after the earthquakes. And now we are dealing with tsunamis with two colleagues, Anne Lemoine and Elisa Lassen. So I give you the floor.
Thank you. So good morning. So I will speak about tsunami rapid response solutions, and more precisely how tsunami modeling databases can facilitate the development of some tools useful for local crisis management support. So as an overview, I will begin with some context and motivation why we try to develop some such tools. And we will focus on the Tsunalogue tool that we developed at VRGM. And at the end, eventually, of integrating it to GOBEYOND project. And then Elisa will speak about her work on tsunami hazard in Cannes City, in a South of France. So why did we try to develop a tool such as Tsunalogue? So the tsunami warning system is well organized at the global scale, at the ocean scale. So there is, for each basin, a tsunami warning system, which is coordinated by the UNESCO. And it permits detection of earthquakes and then estimation and monitoring of the induced tsunami. And such global tsunami warning system permits also to get some forecasting elements of the tsunami, expected tsunami, in order to give information on what would be expected at some point of the basin. So in case, as Pierre said, in case of a tsunami alert, the authorities need to size up the potential impact on the territory they are in charge of, And so it's important for them to have special indicators to estimate the characteristics of the tsunami expected. So what about the idea of utilizing some existing tsunami database to support this local crisis management teams? So the objectives are simple. So at the scale of a territory, at the local scale, it's to analyze some existing tsunami previously simulated databases, simulated from scenarios. And also, it's important to take into account the local authorities' needs and to process some tools that should be useful for them. And it's also important to organize a simple workflow linking the built-in of the alert to those previous simulations. So the idea is not to interfere in the alert, but to provide some elements to interpret it. And then it was important also to try to furnish an automatic report synthesizing the elements that we can propose. So what about the tsunami tool that is still a proof of concept that was developed in BRGM? So it was a request of the French department responsible for managing civil protection. And their request was to provide an easy-to-use decision-making tool for a quick analysis of the potential consequence of the tsunami. So the tool was at first developed for Martinique Island, which is a French island in the West Indies, where first there were some existing database, including many simulated tsunamis from scenarios. And then there were a need for local crisis management actors. And these needs were expressed they need a tool to help the decision making in an eventuality of the emission of a tsunami alert built-in from the PTWC. Sorry. So in summary, our aim was, in case of a tsunami alert, to build a decision support rapid tool that will be hosted in the platform developed at BRGM. And it was to exploit and enhance previous work. And at a glance, this is how work this tool. So we have two inputs. At first, the built-in of alert emitted by the official tsunami warning system, and then the simulated tsunami database. And the tool is an online tool that performs an analog research, search the closest event from the database, closest event of the real earthquake at the origin of the alert. And then the workflow is looking at the previously computed tsunami at the coast of the island, and permit to build automatically online interactive mapping PDF report summarizing the elements. So if we focus on the input data of the Tsunalogue tool, there are of both types. At first, the simulated tsunami database that were from previous work performed a few years ago. So from a catalog of seismic rupture scenarios, credible scenarios, all around the Caribbean basin and Atlantic basin. There were some modeling strategy decided, integrated some 3 generations of tsunami: generation, propagation, and flooding. And at the end, this work permits us to have several outputs And for Tsunalogue, we used the grids of maximum sea surface elevation for each scenarios that were modeled. And this set of models were, for Tsunalogue purpose, post-treated in order to get some parameters that were interesting for the decision makers. So we had discussions with them, and we could, for each coastal segments around Martinique Island, get the arrival times, maximum sea surface elevation, polarity of the initial movement of the tsunami, number of waves, and period of these waves. And as I said, these elements were available for each scenario, each modelization, and available at coastal segments that were decided after a fine analysis of the results. The second input of Tsunalogue are the bulletin emitted by the official and regional tsunami warning system, and they are received that people in charge of the alert, and they are including, I think many people know what they content. So there is some description of the event at the origin of the tsunami. There is a description of the threat level and some elements regarding forecasting and recommendation actions. So how does Tsunalogue works? So it's an online tool, still in development. It's a proof of concept. So it's supported by a Bergen's platform, Vigirisk. And the functionalities and outputs were discussed with the future local users. And still now it's processed manually by the person in charge of crisis management at the local level. So from when he received the tsunami warning system bulletin, its input is considered as an input of the tool, and the tool is performing an analog research between magnitude and localization of events. And from the analog events of the database, the tool performs some cartographic analysis in order to represent potential tsunami characteristics at each coastal segments. So what about the outputs? There are three kinds. So Tsunalogue permits to have at first an interactive map of the results for each coastal segments, where some statistics of few parameters are available, number and period of wave, sea surface elevation, maximum sea surface elevation, etc. There is some SEISAID files to be downloaded, and a PDF report that summarizes the elements of the alert, the results of the workflow, and the warnings, the principal context and limits of the tools, the date, and also a previous preliminary analysis of the analogy between the real event at the origin of the alert and the scenario analog. So what are the advantages of this tool? It's that it permits to provide a local analysis of potential tsunami characteristic adapted to end users from tsunami simulation campaigns, which included fine simulation tools and ad hoc data. And so it also used some existing studies and exploit them in order to help decision makers. Also, it's a rapid and simple tool. However, there is some strong limitation, so it's still in development, and we have to work on analog research processes and to enhance the tsunami database. And in order that, in particular, in order that the analog research would be relevant, this database needs to be very rich, representative, and to include the whole spectrum of possible earthquake that could generate a tsunami. And also, it's very difficult to define the reliability or the uncertainty between the consequence of an analog event and a real tsunami. So what about the prerequisites for a local implementation? At first, it should be the expressed needs of local decision makers. And then it will be the availability of such a representative tsunami database that would include fine modeling processes and local data. So as a summary, what should be the contribution of Tsunalogue tool? Its aim is not to interact with the ongoing tsunami warning system, but to maybe complete the information at local scale. So as an example here is some products of for an exercise of tsunami warning system for Caribbean basin. And so you have the bulletin at the top left, and then a map of forecasting results of the system, and that gives some information of the tsunami characteristic at large scale level, here represented by polygons. And Tsunalogue, however, is more focused at a more local scale and can provide information at the scale of coastal segments associated to a kind of susceptibility of tsunamis. And it also take into account different and more ad hoc simulation characteristics. What about integrate Tsunalogue to GOBEYOND? Look, as I already said, we need at first to interact with local actors in order to be sure that there is some needs and what are these needs. And also not to interfere with existing tsunami warning systems. For Mediterranean, there is a very well-organized system, including the French Tsunami Warning Center, the SEISAID. However, for Mediterranean, and especially for the around cities of Nice and Cannes, we already worked in the past, and we have some tsunami simulated databases that are available that could be eventually used. And then I will let Elisa speak about her work.
Hello, everyone. Nice to be here. So I am a postdoctoral researcher at BRGM, and my work consists of identifying tipping point for first and second responder. So in the southeast part of France, the tsunami hazard, we have tsunami risk that come from two sources. One is the Ligurian Fault between France and Italy. And we also have the Maghreb's Fault in the north of Algeria. And on the right map, you can see the Mediterranean coast, and you can also see Cannes in white. And we did several scenarios, both from the Ligurian Fault and from the Maghreb's Fault. And we kept the scenario for which the tsunami height was the highest along the shore. And here we focus on Cannes. So let's take a look at what's happening around the city. Oh, sorry, I forgot to mention here for Cannes, the most impactful scenario was the one coming from the Maghreb's Fault. So it was a tsunami generated by an earthquake of magnitude 7.8. So we keep this scenario for the next analysis. So here you can see the city of Cannes on the left map. You can see, I will try to show. Here you can see the Palace of Congress. And here you can see a piece of the Cannes airport. We built some isochrones, so the first and second responder can see how long it takes for them to commute. From the moment the tsunami is detected to the moment the population receives the alert, it can take about 1.5 hours. So it's still important for the next hour to see how long they need to commute. And if we focus here on the biggest tsunami envelope, we only keep tsunami height above 50 centimeter. And why is because above 50 centimeter, emergency vehicle cannot circulate anymore. So that give first and second responders some clue where they should prioritize evacuation. And you can see that in this envelope, we have about 10,000 residents and almost half of them are seniors. So evacuation can take some time. We also have children. We have 2 primary schools. So it's important to know whether or not they are ready to evacuate. And finally, we have some car park, underground parking, public tunnel. And from experience, we know that people tend to try to get their cars. So it's important for first and second responder to also know that those areas can be flooded. So yeah, this is just a quick example to show you how tsunami simulation can be a powerful tool for first and second responder and how this can help them to optimize their evacuation strategy. Looking forward to discuss this and thank you for your attention.
Thank you, Elisa.
So maybe we are late and I will skip the conclusions.
Sorry.
No, but
Here.
okay. So in few words, as a conclusion, so we show you that we developed an adult solution for tsunami rapid response, and at local levels, and that would be a tool in complement of the basin scale tsunami warning system. And this tool is focusing on tsunami characteristics on coastal segments of the local scale. And it's still a proof of concept that is already, however, it is already used in Martinique during some exercises that are very brave. So as a perspective, we still need to enhance our simulated database. That is, the tool would be more powerful and more precise and more relevant if this database is representative of what could happen. So we also need to continue to propose a better uncertainty analysis to have a good representation and simple representation of the reliability of the results we can provide. And so it's still in development. So it's still a proof of concept. And we have to work, for example, on the algorithm of the analog research. And finally, as a more longer perspective, we should think, depending on the needs of the local actor, we should integrate some geographical analysis and some hazard or risk analysis in such tool. And why not try to integrate some elements about onshore information in case of flooding. So thank you very much.
Thank you to both of you. So last but not least, we now deal with the phenomenon of landslides due to rainfalls. So a mix between geo and weather hazards. So please, Séverine, the floor is yours.
So good morning, everybody. So this is the last talk about landslide. The elements I present you are supported by GOBEYOND project, but also by another one, Vivement project, which is financed by the French National Research Agency. And you can see that this work is performed by a lot of colleagues from different institutes. You can see here in the slide. So I will briefly introduce the context and the motivation of the project. Then I will present you the landslide early warning system that is currently developed within Vivement project. Then I will propose you a focus on the extension of this early warning system to a European level, performed by my colleagues from UPC. And then finally, the next step of this current work. So first of all, there is more and more studies that reveal that climate change may have significant impacts on landslide activity. Since the most important triggering factor is the hydrometeorological forcings. The recent catastrophic flooding that occurred in valleys during Alex storm in 2020 illustrates also the high damages that landslide may induce. So there is a need to improve hazard assessment and risk mitigation. And amongst the solution, early warning system constitutes a key challenge to anticipate the phenomena. In this work, we focus only on shallow landslide, not deep-seated landslide, which are generally triggered by rainfall. There is still some issue in this topic. There is a difficulty in prediction because of the complexity of the phenomena controlled by numerous parameters. So there is still a need to improve knowledge on the landslide triggering conditions. So the main objective of the project is to develop a landslide forecasting system for safety authorities in mountain areas. For that, 3 key issues are addressed through this project. The first one is to define and to analyze the different needs and acceptability of stakeholders regarding early warning system at general and in particular for the landslide. The second topic is to quantify the different components of landslide hazard. And finally, to develop an operational forecasting and warning system. So this project is based on a multi-scale approach by considering both local and regional scales with the development of services to both scales for the end user. So in particular, the departmental and municipalities civil protection services, and also fire and rescue departments. So the objective is to have operational benefits for the users with an early dissemination of information and decision support messages, and to activate in an early phase the safeguarding plan at municipality level and an earlier securing of the exposed assets. So the first step is to address the different needs and acceptability of stakeholders. So for that, several surveys have been conducted among stakeholders in charge of local civil protection to gather different information regarding risk perception, local risk prevention, and also the current crisis management as it is done at that moment, and also their needs concerning early warning system for natural hazards and in particular landslide. So it is very important for this project that the end user are very implied within the process of the project during all the project, and because they help us to define their needs, but also to improve the service we are developing. So there were numerous information that we obtained from this survey, and amongst them, it is clear that there is a necessity to improve the knowledge on what to do within crisis management at the municipality level for landslide phenomena, but also for other natural hazards, such as meteorological events and flooding. They are also clearly indicated that they have also the need for information, general information on landslide, and also information and forecast on landslide hazards. The second step of this work is to quantify the different components of landslide hazard. So that means the different steps are the quantification of the rainfall triggering landslide, which permit to define, in particular, rainfall thresholds. So these analyses are based on landslide inventory and meteorological data. I will show some results in next slide. Then we have to specialize these thresholds with integrating other information, such as geomorphological features. So one way to do that is to integrate shallow landslide susceptibility maps. I will show also some information on that. Then the third step is to integrate the propagation of the landslide themselves to know which area could be reached by the phenomena. And then we have finally to couple all these components with precipitation forecast in order to get a spatiotemporal forecasting system. So this is the current results. The project is still in progress, so we are not at the end of the project. So this work is focused in French Alpes-Maritime department, where we get a large inventory of shallow landslide, as seen here. So we have almost 5,380 shallow landslide. The analysis is focused on 3 types of landslide: the road embankment, mid-slope, and flow-like landslide. And among these events, we have also focused our analysis on an extreme events, the Alex storm, which happened in 2020. So as you can see here, this event was a huge one with precipitation higher than 500 millimeters in 24 hours, and with a lot of impacts in 3 valleys in this territory, in Tinée, Vésubie, and Roya Valley. This phenomena induced a lot of landslide, more than 1,600 events. And so the objective was to analyze if these events, how this kind of events can modify the quantification of the hazard itself. So first of all, we have analyzed the rainfall triggering condition from rainfall data provided by Météo France. So with an algorithm developed by CNR from Italy, Control T, we have defined the rainfall events that trigger landslide, which can be characterized by cumulative rainfall and duration of the event, as you can see here. And for each landslide, we have defined these parameters. And based on these elements, it is possible to define a threshold through a frequentist approach combined with bootstrapping to define thresholds on these events. And so what you can see in this figure is that depending if you consider extreme event or not, the thresholds are completely different. So these results highlight the impact of extreme events in early warning system design. So it is important to consider that. Another subject concerns also the landslide susceptibility maps. We have also performed some maps based on a random forest approach with considering different predisposing factors such as lithology and different parameters deriving from elevation model. And so I don't go into detail, but what I also wanted to show here is that depending if you consider extreme events or not, the landslide susceptibility is different. And not only in the area where the event appears, but also in some other parts. So here there is also the necessity to carefully consider the extreme events in designing early warning system. So the next step is to couple all the different components of hazards with precipitation forecast to get a landslide forecast in real time. And finally, to develop an operational forecasting at a local scale. So to define alert levels, the messages, and the associated action at the adequate spatial resolution. So that has to be done in next months. And these tools will be implemented within Wikipredict platform in the next months or so. So now I change the scale of analysis. So this is the work of my colleague from University of Catalonia, UPC, who have performed a development of a real-time landslide early warning system at the scale of Europe. So you can see here the different components of this system with static inputs, with the susceptibility map. Then the system introduce a real-time precipitation and analyze them. And so based on rainfall thresholds, the system evaluates the 24 hours of precipitation to identify the rainfall hazard level for different written periods. So once it is done, the system is integrate rainfall hazards and susceptibility level into a warning level matrix, as you can see here, to generate a qualitative warning for shallow landslide and debris flow. So the system is still in progress, but this is an example of the input component with the susceptibility map at the European scale provided by GRC teams. You can see here the real-time precipitation coming from Opera radar, and then the resulting landslide warning level at the European scale. So once it is done, so it is still in progress, but the performance of the model has to be evaluated. So for that, it is useful to compare the early warning level, the early warning message to reported landslide events. So that has been done in different areas of Europe, in the French Alps Maritime, in Catalonia, in Spain, and also in Bosnia and Herzegovina region. And so an example in Alpes Maritime in France, we have compared the landslide warning level with the reported landslide during an event that appears in November 2017. And we can see that the system successfully captured 93% of the landslide events. So the next step, finally, is of course to finalize the regional early warning system. There is still some steps to continue and to finish. Then the system will be locally applied through a GOBEYOND project at 2 municipality scales in Guillaume and Sospel municipality. And then what is proposed through this project is to integrate the landslide hazard layers with map of exposed elements, such as built areas, but also road infrastructure. And for the European landslide early warning system, the objective is to continue the evaluation and of the performance of the model. And in that way, the objective is also to compare the regional early warning to European early warning and to improve it in that way. Thank you. I finished.
Thank you, Céline. Thank you to all of you. The next workshop coming in Italy and Napoli. It's not a webinar; it's a presential workshop in April, and it's possible to register. So feel free. Thanks to everyone, and see you. For some of you in Italy, in Napoli, or to exchange by email. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.
Bye bye. Thank you.
Bye. Thank you.